Hi, this is Tzvi Rosen with another lecture in our course on matrix theory. When we first spoke about matrix transformations, I gave some examples that related to geometry in the plane. This lecture is really going to take that to the next level, go into it fully, and then talk about composition of these matrix transformations and how that relates to matrix multiplication. So let's get started. Okay, so we'll remind you what the standard matrix of a transformation is. So we have a transformation T, and then it maps from our, I always forget which I want to put first, M or N. Let's say it's N to Rm. Then there's a matrix associated to this, which is equal to an M by N matrix, whose columns are as follows. Okay, column 1 is what you get when you apply T to the first basis vector. Column 2 is what you get when you apply it to the second basis vector, etc., up until column N, where you write what you get when you apply T of En to when you apply T to En, the nth standard basis vector. What this matrix allows us to do is, if we want to see what TV is, all you need to do is multiply A by V. Okay? And the linearity of this operator, so we're assuming this is a linear transformation. That guarantees for us that this matrix will correctly compute the value of T. So we start with reflection, which takes a line in the plane, okay, and we're working in R2 to start. Takes a line in the plane and it flips the plane over that line. So the stuff that was above is now below, and the stuff that was below is now above. And we want to keep everything's kind of relative positions the same, except that they flip relative to that line. So to get the standard basis, so let's first think about reflection over the x-axis. So the picture of what's happening here, we have our two basis vectors, E1 and E2. After we apply T, which is, so let's say this is Tx. So Tx of E1 is just the same as what you start with, because when you reflect over the line, it started in the line and now it's still in the line. On the other hand, when I reflect E2 across this line, now it shows up on the other side. This is Tx of E2. Okay? So the standard matrix here is going to be, in the first column, you write what the value of Tx of E1 is, and since it doesn't change, it just stays as the first standard basis vector. As for the second one, we get 0, minus 1. Okay? Because now, instead of having E2, we have minus of E2. Okay, what if we do the y-axis? So we'll call this one Ty. Okay, so how does this affect our two basis vectors? Well, the y vector will stay the same because it's sitting on the line of reflection, so it just sits in that line, doesn't go anywhere. On the other hand, E1 goes to the other side, and now that's Ty of E1. Okay. So if I want the standard matrix there, what it's going to be equal to is the value of E1 in the first vector, in the first column, which is -1 and 0, because you get the minus of the first vector, whereas the second vector stays the same, so it's just 0, 1. Okay? So if I want to know, for instance, for a random v, so if I want to know what's ty of v, that's going to be equal to, and let's say it's v1, v2. All I have to do is plug it into this matrix, -0, 0, 1, times v1, v2. And we'll see that the correct output of that transformation will be -v1, v2. Okay? Cool. Now let's think about a slightly more complicated reflection. Here it's over the line y equals x. So we have the line y equals x here. And again, the way we're going to do this is just by computing the action of this transformation. So let's say this is t is root t of v equals reflection over y equals x. Okay, and you might ask, how do I know that this is linear? Maybe it's not linear. That would be a legitimate question, but take it for granted for right now that this is linear. And so now let's see how this acts on the basis vectors. So if we have E1 here and E2 here, then T swaps these two vectors. Okay, so the output is this vector t of E2, and this vector is t of E1. Okay, so in terms of the matrix, what we'll get is 0, 1, because the output of t when we plug in E1 is E2. So we put in the second standard basis vector in column 1. And the second column is 1, 0, okay, because that's what we get when we plug in the second basis vector. We get out the first basis vector. Okay? So that is reflection over the line y equals x. And now let's get even more complicated. So now we have a line through angle theta. Okay, so here's our picture. Draw it a little bigger so we can use the geometry. So let's say we have a line passing through the origin with angle theta from the positive x-axis. Okay, and now we want to figure out what is the correct reflection for each of our basis vectors. Okay, so this is E1. And this is E2. Okay. So in terms of what the correct reflection is, first thing we want to note is that this angle is going to be pi over 2 minus theta. Okay? Because it's the complement of theta in the in that first quadrant. Okay, so we'll note that when we try to reflect over this line, the angle is going to be, the angle that E1 makes with this line should be equal to the angle that T of E1 makes on the other side. So what I should expect here is that E1 should map to something with angle theta over here. Okay. And as for E2, same idea. We'll put so this should be T of E1. Let's call it T theta. And this will be T of E2. and it will be pi over 2 minus theta in this direction. Okay? So now what we have to do is figure out what these values actually are. Okay? So meaning what the coordinates of these vectors actually are. So we'll start with t of E1. So t of E1 is basically what you get when you when you rotate E1 theta up to the line, and then another theta, okay? Rotation by 2 theta. Okay, so let's put that over here. So if we have t of E1 here, and this is 2 theta, and we know that E1 has length 1 because the length of the vector shouldn't change when you do a reflection. So what we'll get is cosine 2 theta here and sine 2 theta here. Okay. So this is going to be the vector given by cosine 2 theta, sine 2 theta. Okay. How about the other vector, t of E2? So we have so this is going to be t of E2. And we know that the angle is going to be, so the angle from this line is pi over 2 minus theta. So we start from an angle of theta, and then we subtract from it pi over 2 minus theta. So this angle is going to be, I want the angle from the x-axis. So this angle is going to be theta minus pi over 2 minus theta. Okay, so that's another way of writing that would be 2 theta minus pi over 2. So t of E2 equals rotation, or rather, it's the vector at angle 2 theta minus pi over 2. So the coordinates of that are going to be cosine 2 theta minus pi over 2 and sine 2 theta minus pi over 2. Using properties of sine and cosine, this is sine of 2 theta, and this is minus cosine of 2 theta. Okay, so to get the standard matrix for reflection over the line through angle theta, you would take these two vectors, cos 2 theta, sine 2 theta, and sine 2 theta minus cos 2 theta, and plug them in. Sorry, this should be cos 2 theta, sine 2 theta, and sine 2 theta minus cosine 2 theta. Okay? And if you want to know the general form for a vector that's been reflected over such a line, so t of v is going to be equal to, and let's give it a specific, so t of v1, v2 will be given by the vector that's just the multiplication of this vector. So let me copy this. Okay, make it a little smaller. Multiply this by v1, v2. And that gives me first coordinate v2 cosine 2 theta plus, sorry, it should be v1, yikes. v1 cosine 2 theta plus v2 sine 2 theta. As for the second coordinate, we get the multiplication of the second row by the column, get v1 sine 2 theta minus v2 cosine 2 theta. Okay, and that's what you get after reflecting over a line through angle theta. Okay, so we've talked a lot about reflection. Now let's go to another natural geometric operation, which is rotation. So let's say I have my standard basis vectors, e1 and e2, and I want to rotate them by 90 degrees. Okay, so this is where e2 goes, and this is where e1 goes. So this is t of e1, and this is t of e2. Okay? Okay. So t rotates the plane 90 degrees. So its matrix is given by so let's compute the standard matrix just using the picture we just drew. First column, you put the image of e1, which is this vector, so it's the upward pointing vector, which is 0, 1, right? Because it's the second basis vector. As for t of e2, that's the same as e1, but it's pointing backwards, so we get minus 1 of and 0. Okay, so this is the matrix you would get for rotating a vector, for rotating the plane 90 degrees. So if we wanted to compute, for instance, t of v1, v2, okay, that's going to be equal to 0 minus 1, 1, 0 multiplied by v1, v2, and we would get minus v2, v1. Okay. How about rotating through an angle theta? Okay, so this is going to be a similar exercise to when we were reflecting over a line through an angle theta. So let's draw our basis vectors, and now let's understand what it looks like when we apply t. So this is e1 and e2, and now we're going to apply t, and we're going to get t of e1. Okay, that's going to be angle theta, and then we're going to get t of e2, also angle theta. Okay. So what are these? How can we write down the coordinates for these vectors? The same way we did before. So t of rotates by angle theta. So t of e1 is going to be equal to, drawing the right triangle, we get the x-coordinate will be cosine theta, and the y-coordinate will be sine theta. And then doing the same exercise over here, we have t of e2 will be minus sine theta, okay, because horizontally you have sine theta pointing to the left, and then as for the vertical component, that's cosine theta. Okay, so our matrix will be, again, you put t of e1 in the first column and t of e2 in the second column, so we get t, so this will be the standard matrix for t. We get cosine theta, sine theta, minus sine theta, cosine theta. And that's a rotation matrix through any angle theta. Now we'll talk about something you may or may not have seen before called orthogonal projection. And the idea here is that we're in the plane and we fix a line. So let's say we fix the x-axis. And then for any point, what we're going to do, or for any vector, I should say, what we're going to do is just drop a right angle here. Okay? And then this is going to be the output of the orthogonal projection. Okay, it's just what you get when you drop a right angle to the specified line. So if we're doing Tx equals orthogonal projection to x-axis, this is what it would look like. So how can we compute the standard matrix for this? Well, it's pretty straightforward. You apply it to the standard basis vectors the way you normally would. So E1 and E2. Okay. When we take Tx of E1, because it's already in the x-axis, it stays the same. Okay. As for Tx of E2, that, when you drop the orthogonal, drop the right angle to the x-axis, you get the 0 vector. So this maps to 0. So that means that the standard matrix for Tx is going to be 1, 0 in the first column, because that's the value of E1, and 0, 0 in the second column. Okay? Okay, what about Ty? So if Ty is orthogonal projection to the y-axis, then Ty of E1 is 0, right? Because you're mapping everything to the, so this is Tx, and this would be Ty. Ty of E1 will be 0, while Ty of E2 will be E2. Okay, so this is the standard matrix for, this is for Tx. For Ty, the standard matrix is going to be 0, 0, 0, 1. Okay? So now we're going to orthogonally project onto a line through angle theta. So we're going to need to be pretty careful with the geometry here. So I'm going to draw a big picture. Actually, maybe let's make it even, let's focus on the first quadrant. Okay, so we've got a line through angle theta. Okay, so this angle is theta. This angle is pi over 2 minus theta. And as always, what we're really interested in is what the images of our basis vectors are going to be. Okay. So the way that orthogonal projection is defined is you're always dropping a right angle. So we want to drop a line which is perpendicular to the line that we've specified. And the same for this. Okay. And these are going to be right angles. And now what we want to do is understand what the coordinates of these 2 points are. One way to go about that is to find this length and this length. Okay? By finding those lengths, because we already know what the angle is from the x-axis, we'll be able to put that together to find the coordinates. So let's call the length from, we'll call this length A, and we'll call this length B. Okay? So it's from the origin to the orthogonal projection of the two. Probably should have ordered them differently, but it's fine. We'll keep it straight. So this is E2. Sorry, this is E1. This is E2. And this is T of E2. And this is T of E1. Okay. So now in order to figure out what these lengths are, we want to use the geometry of right triangles. So we know that since this lower angle here is pi over 2 minus theta, then this upper one is theta. So we'll focus on that angle when we're looking at E2. But let's start with B. So if B is in this right triangle, we know that these two lengths are 1, okay, because they're the basis vectors. So what we're looking for is a trigonometric function which involves b and 1. So relative to theta, b is the adjacent side, and 1 is the hypotenuse. So what this tells us is that cosine theta equals b over 1. Okay, great. So we've solved for b. How about for a? So with a and 1, so with theta, a is the opposite angle. So, and 1 is still the hypotenuse. So we have sine of theta equals a over 1. So now we have a is going to be sine theta. Great. Okay, well, if I know that length, how do I compute the coordinates? Okay, so let's go to the next slide. So we know that we have this line of direction theta, and I know that I have a vector of length of length sine theta here. So this length is sine theta. So how do I compute the coordinates? Well, if it's sitting on a circle of radius sine theta, and this angle is theta, we know that in the circle of radius 1, these coordinates are cosine theta, sine theta. Okay, that's where it's 1. So what that would mean for us is that this is going to be coordinates cosine theta, sine theta times sine theta, or just sine squared theta. Okay? Because you're scaling cosine theta, sine theta by sine theta. So the output here is t of E2 equals cosine theta, sine theta, sine squared theta. Okay, how about t of E1? So the length there was cosine theta. Maybe I'll just okay, so let's do this similarly for t of E2. Okay, we'll do similarly for cosine. So we have a length of cosine theta along this line. So this is cosine theta. And now I want to compute the coordinates. Well, it's going to be a scaling of the same vector. So this is our circle of radius 1, and this is cosine theta, sine theta. Then this point is going to be cosine squared theta, cosine theta, sine theta. Okay, same argument as above. So t of E2 is cosine theta, sine squared theta, and t of E1 is equal to cosine squared theta, cosine theta, sine theta. Okay, and we can put that into our standard matrix. So T gives us the standard matrix cosine squared theta, cos theta, sine theta, cos theta, sine theta, sine squared theta. Okay, and that's how you would compute an orthogonal projection, by using this matrix for any vector you're given. Okay, here are two very easy matrix transformations. These are contraction and dilation. This is what happens when you just make everything bigger or smaller. So contraction is where you multiply every vector by some k greater than 1. So sorry, that's dilation actually. Dilation is where you take k greater than 1, and then t of v is kv for all v. Okay, and plainly the matrix that would give you is k, 0, 0, k. Because same idea, you look at the basis vectors, and it scales both of them by k. As for contraction, this is the same thing, but just with k less than 1. Okay, that's pretty straightforward. So then you can get a little trickier by saying, hey, I just want to stretch in one direction but not in the other. So let's say I just want to stretch in the x direction. So now x gets scaled by k and y stays the same. So that looks pretty much the way you would expect it to. So something like if you have something like this, and now, so this is your unit square, and then you kind of scale in this direction. It grows out more. So this is k times E1. So compression is where, let's start with expansion. Expansion is where k is greater than 1. And the matrix that you get is just what it looks like. You get standard matrix K1. Okay, and the same is true for compression. It's just compression is where it has k less than 1. Okay. Great. So that covers everything I was going to do in 2 dimensions. And now we can talk about 3 dimensions. So the first thing I want to do in 3 dimensions is rotation. But you have to settle some convention about which way you're rotating. So if I give you some positive angle theta, are you going to go, what's the corresponding notion of clockwise or counterclockwise when we're sitting in space? So the way to do it is you'll be given some vector. In this case, it's u. And the positive rotation for angles relative to that u is the way your fingers curl when your thumb points towards points in the direction of u. Okay? And when your thumb points opposite u, your fingers curl in the negative rotation direction. Okay. So let's look at rotating around the positive x-axis in R3. Okay, so what does that look like? Well, if this is my x and this is my y and this is my z, what we'll be doing is kind of making everything circle this axis. So you kind of, the x is kind of staying the same, but then everything is kind of shifting around it. Okay. So this is our t. So we want to see how does t act on each of the basis vectors. So here now we have 3 basis vectors, E1, E2, and E3. So E1 is along the x-axis, and I note that I didn't specify the angle we're rotating through. Let's say we're rotating angle theta. Okay, so t of E1 stays constant. This is E1, because that's the axis of rotation. T of E2, well, we have the YZ plane. And so we want to be thinking about rotating in the YZ plane. So Y is going to be rotated, so rotation of theta in YZ plane. And for E3, we're going to have rotation of theta degrees also in the YZ plane. So what we can do now is for E1, we just put a 1, 0, 0. Okay, that's the image of this rotation on the first basis vector. But for the other basis vectors, because we're looking at rotations in the YZ plane, we can scroll up until we find rotations in the YZ plane right here. And we can just use this standard matrix and plug it in, right? Because everything was working in the YZ plane. So we have 0 cosine theta minus sine, or sorry, this should be sine theta, and 0 minus sine theta cosine theta. Okay? And that is the matrix for rotation in about the positive x-axis in 3 dimensions. Okay? The x part stays the same and the yz part changes. Okay, so what if we use the positive y-axis? It's similar, but you have to be a little careful about orientation. So here, so if we're doing rotation about the positive y-axis, okay, think about the right-hand rule. So the y, it's going to be coming kind of towards you when it's on the upside, and then away from you on the underside. Okay. So that's the rotation we're looking at. So t of E2, as in the last example, this is just going to be E2, so that stays the same. T of E1, so we're not rotating in the standard way in the xz plane. We're actually rotating in a negative direction in the xz plane. Rotate by minus theta in xz plane. Okay, and similarly with E3, rotate by minus theta in the xz plane. So what our standard matrix becomes will be, well, the second column is easiest, 0, 1, 0, but I need space for t of E1. So we're rotating by minus theta, so that's going to look like cosine of minus theta. The y-coordinate doesn't get affected because we're in the xz plane. And then sine of minus theta. Then we have 0, 1, 0. And then we have minus sine minus theta, 0, cosine of minus theta. Okay, and hopefully you remember that cosine is an even function and sine is an odd function, so we can get rid of these minus signs by doing this. Cosine theta 0 minus sine theta, 0, 1, 0, sine theta, 0, cosine theta. Okay, and that's rotation about the positive y-axis. And I'll leave the positive z-axis as an exercise for you. And I actually have to pause there for a moment. Hi, I had to switch locations, but we're back up with the lecture. The next transformation of R3 that I want to discuss is contraction dilation, and this is really the same story as it is for R2. We have t acting on any vector by multiplying it by kv, if k, by k. So if k is less than 1, this is called contraction. And if it's greater than 1, it's called dilation. Okay, and since it acts on E1 by multiplying it by k, and it acts on E2 by multiplying it by k, and on E3 by multiplying it by k, the standard matrix is the 3 by 3 matrix with k's on the diagonal and zeros off the diagonal. Okay, so that's contraction and dilation. That is not so interesting. Orthogonal projection. So we saw orthogonal projection onto lines, but we can also orthogonally project onto planes when we're talking about 3D. So if we have our 3D axes, and this is x, y, and z, one thing you could do is fix one of these, fix a plane spanned by 2 of the coordinate axes. So for instance, this plane. Okay, so let's say we want to look at this plane. And then orthogonal projection can take a point and just map it directly down into the xy plane. And the way that this works is it takes t of x of a coordinate, let's say a vector of the type v1, v2, v3, is just going to return the first two coordinates, and the last coordinate is going to be 0. So it'll be v1, v2, and 0, right? Basically fixing its position in the xy plane, but in terms of xy coordinates, but then sending it down to the xy plane by sending the z coordinate to 0. So in terms of its action on the basis elements, on the basis vectors, we have t of e1 equals e1, t of e2 equals e2, and t of e3 equals 0. So the orthogonal projection has standard matrix as follows. Standard matrix. First column is e1, second column is e2, and third column is the 0 column, because that z-directional vector gets squashed. Okay? And that gives us the matrix of our transformation. Okay, so that's all of the R3 transformations I wanted to talk about. And now I want to talk about putting these maps together. Okay, so we've spoken about how these transformations have geometric interpretations. Okay, but what if we want to do a few different geometric things in a row? So if we want to take T1 and apply it to a vector. So let's say we have, okay, now we've been talking about R2 to R2 and R3 to R3, but you can also just map to different spaces. So let's say we have Rn is mapping to Rm, which is mapping to Rk. Okay, and let's say this is T1 and this is T2. So if I take a vector in here and I pass it through this map, okay, so I get T1 of V, I should be able to pass it through this map as well to get T2 of T1 of V. Okay? And this map that we get by going around this way, just going straight to T2, T1 of V, is called the composition, T2 of T1. Okay? And so you'll notice that even though you're doing the map T1 first, you list it to the right because you want it to be closer to the vector. So that's why you do the ones that are closer to the vector first, and you move out as you go. So order flips. So just be careful about that. Caution. Okay. So how do I get from, so I know that I can represent transformations as matrices. So T1 and T2 have standard matrices. Let's call those M1 and M2. So how can I get the standard matrix for T2 compose T1? So T2 compose T1, as you probably guessed from the title of the slide, has standard matrix M2 times M1. Okay? So just double check for yourself that this makes sense in terms of the definition of matrix multiplication. So M1 corresponds to T1, so that it maps from Rn to Rm, so that's going to be an M by N matrix. Meanwhile, M2 maps from Rm to Rk, so that's going to be a K by M matrix. As we know, the inner coordinates have to agree, the inner dimensions. So the second dimension of the left-hand matrix and the first dimension of the right-hand matrix. And indeed, these two agree. So we are at least well defined in terms of the matrix multiplication. Okay, so let's see how this would work in practice. So let's say we were going to let's say we were working in R2, and we want to rotate our vectors by pi over 4, then project onto the x-axis, then dilate by 3. Okay, so just to give you a picture of what that would look like, so we have some vector v, and this gets rotated over here, and then it gets projected onto the x-axis, and then it gets stretched by 3. So we do a bunch of different steps here and eventually get to a new vector. The question is, can we write down the matrix for this new transformation? So we can, and we're going to do that by writing down the matrix for each of these. So rotation by pi over 4, we know that rotation has the formula cosine theta, in this case pi over 4, sine pi over 4, minus sine pi over 4, cosine pi over 4. Okay, and this gives us, if remembering your trigonometry, cosine and sine of pi over 4 are both 1 over square root of 2, or square root of 2 over 2, whatever you prefer. I prefer 1 over square root of 2. 1 over root 2, 1 over root 2, minus 1 over root 2, 1 over root 2. Okay. And if you prefer, you can even simplify this a little bit by just factoring out the 1 over the square root of 2 and have the matrix 1, 1, minus 1, 1. Okay. Projection onto the x-axis, this is the matrix 1, 0, 0, 0. Okay. As for, I'm going to move this over. As for dilation by 3, we know this to be 3, 3, 0, 0. Okay. So we have 3 matrices, and we can multiply them. So we obviously have to do this in order. So we're going to do, if this is our T1, and this is our T2, and this is our T3, what we're looking for is the standard matrix of T3 compose T2 compose T1. Okay. And that's because whatever starts on the right, that's the first transformation you're doing. Okay, so let's multiply these matrices. I'm just going to write them all out. We have 3, 3, 0, 0, 1, 0, 0, 0, 1 over root 2 times 1, 1, minus 1, 1. Okay, so straightforward multiplication, we get these two together multiplies to 3, 0, 0, 0, and 1 over square root of 2 times 1 minus 1, 1, 1. So the scalar you can always move around. But let's do this matrix multiplication. We get, we'll keep the 1 over square root of 2 out here. And then we have 3. That's the first row dotted first column. First row dot second column is minus 3. Second row, because it's going to be 0, it's just zeros. And so we get the matrix 3 over root 2 minus 3 over root 2, 0, 0. And that is the matrix for our transformation. Okay. So one thing that's important to know is that general transformations do not commute. That means that the order that you do these in actually matters. So for instance, reflection about the x-axis and 90-degree rotation. Okay, so let's say I take a vector. The question is it important which order we do this in? So let's say I reflect about the x-axis, so that will send me down here. Excuse me. And then I rotate 90 degrees. That would send me back up here. Okay, so it's seemingly the same spot. Okay, what if I first do a 90-degree rotation and then I reflect? Okay, so let's use a different color to signify that we're doing a different order of operations. So first we would get a 90-degree rotation this way, which would come out to here. And then we would reflect about the x-axis, which would bring us down here. So we would get precisely the negative of the vector that we got by doing it the other way. Okay? And this is reflected in the matrix multiplication as well. So true geometrically, but it's also true via the standard matrices. Okay, so if we think about reflection about the x-axis, we saw earlier that the matrix for reflection about the x-axis, it takes 1 here and -1 here. Okay, and then we have 90-degree rotation is cosine pi over 2, sine pi over 2 minus sine pi over 2, cosine pi over 2, but we know that cosine pi over 2 is 0, and sine pi over 2 is 1. So that will be 0, 1, -1, 0. Okay, and doing out the multiplication, we get 1, 0 times 0, 1 is 0. 1, 0 times -1, 0 is -1. 0 minus 1 times 0, 1 is -1. And 0 minus 1 times -1, 0 is 0. Okay, so we get this matrix. When we do it, this would correspond to doing first, so first rotation and then reflection. Okay. How about the other way? So we would take 0 minus 1, 1, 0, multiply it by 1, 0, 0, -1, and we would get, so first row dot first column is 0, first row dot second column is -1 times -1, which is +1, and 1, 0 dot 1, 0 is 1, and 1, 0 dot 0 -1 is 0. So this corresponds to first reflection, then rotation. Okay, and this shows that that one gives you the negative of the other, just as the way we drew it in the picture. Okay, but some pairs of transformations do commute. So if you take two rotations, so for example, cosine theta, sine theta, actually let's make it easier to write thing. Cosine A, sine A, minus sine A, cosine A. So this is one matrix, and this is another matrix, cosine B, sine B, minus sine B, cosine B. Okay, so these correspond to rotation by A and B respectively. So this is rotation by A and by B. So when I do the multiplication, so let's say I multiply with A on the left and B on the right. So I'm going to write this as MA times MB. This is going to be equal to cosine A cosine B minus sine A sine B. Okay. The next one is cosine A times minus sine B. So it's minus cos A sine B plus negative of sine A cosine B. So it's also, this goes inside of the parentheses, sine A cosine B. Okay. Then the second row first column, we take second row dot first column, we get sine A cosine B plus sine B cosine A. And in the bottom right, we get sine A times minus sine B plus cosine A times cosine B. So this is cos A cos B minus sine A sine B again. Okay. So one thing you could do is just say, what happens if I switch A and B? Because the formulas are the same, so I just have to switch A and B and see if the values in this product change, and they don't. So this is symmetric with A and B, so that means that they commute. Okay? But one thing you can notice going even further is that each of these is one of the angle addition formulas. Right? So the top left, that's cosine A plus B. And the bottom left is sine A plus B. Top right is minus sine A plus B. Bottom right is cosine A plus B. So what this gives us is a way to remember our angle addition formulas. You just do matrix multiplication on the corresponding rotation matrices. Okay, I think that's pretty cool. Okay, now a brief connection of this new material and transformations to null space and some of the things we learned in previous lectures. We have the following theorem from the textbook. If A is an n by n matrix, and TA from Rn to Rn is the corresponding matrix operator, then the following statements are equivalent. Okay, first, A is invertible. Okay, that's the matrix. The kernel of TA, so this is the transformation corresponding to A, is just the 0 vector. And this makes sense because if you have more than one thing mapping to 0, how are you supposed to be able to invert the map? Okay, the range of TA is Rn, so this means that so this is saying that no vector besides 0 maps to no non-zero vector maps to 0. This says that every vector is mapped to. Okay, and TA is 1-to-1 means that every vector gets paired to exactly one other vector. And this is a straightforward consequence of the other two. Okay, so 1-to-1 matrix transformations, to summarize, correspond to invertible matrices. Okay, and that should make sense intuitively too, because if you have some matrix, so suppose A times B is equal to the identity matrix, then the corresponding composition of matrix transformations gives us TA, TB equals the identity map. Okay, TA composed with TB is the identity map, which means that your mapping can be undone. And that's only possible when you have a 1-to-1 mapping. You can send your vector through and then bring it back. Okay, and let's look at some quick examples of which of these are 1-to-1. So rotations are 1-to-1 because just to get back to the previous vector, you just rotate back. Okay, so you can invert rotation by theta by rotating by minus theta. Okay, reflection, this is invertible by just doing it twice, right? If you reflect and then reflect again, you get back what you started with. Reflection is its own inverse. Okay, so both of these are 1-to-1. This is 1-to-1. Orthogonal projection, this is in general not 1-to-1. Because you have a bunch of things mapping to 0. Anything orthogonal to the subspace you're projecting onto goes to 0. So some vectors get squashed. Okay. On the other hand, dilation and contraction is certainly 1-to-1 because the inverse is just multiplying by 1/k. To invert multiplication by k, you just have to divide by k. Okay. And that's it for this lecture. Thank you so much for your attention.